Welcome everyone to our 2026 Insider webinar series. Today we are shattering the ceiling as we explore quantum-inspired engineering with BQPhy. We have a packed 90-minute session ahead of us, so looking at how frontier technology is meeting practical engineering today. It's all right if you're not from engineering background. If you're here to just explore what quantum is, that is absolutely fine. But if you are an engineering student who've worked with any of the quantum inspired or any of the quantum technologies before, you are in the right place. All right, so let's move on. So my name is Elijah. I am the head of Wiser Insider. And today with us, joining us is our primary speaker, who is Ruth Lineswala. He is our Chief Technical Officer from BQP. We are also thrilled to feature a cohort showcase with Jinwhuy Lee. He is a graduate research assistant in aerospace engineering from the University of Maryland. They will introduce themselves more when the time comes. In the meantime, let me share a little bit about what Wiser is. Wiser operates at the nexus of science, industry, and workforce readiness, ultimately bridging students and researchers to firsthand experience to the frontier technologies like BQP. So through our Insider program, we connect cutting-edge computational tools with our leaders of tomorrow. Okay, I think there are some chats going on here, so I'll leave that as it is. Our agenda for today is packed. We have a 90-minute session, includes from housekeeping to speaker introduction and a deep dive into the technology itself. We will cover some of the quantum-inspired vision and practical pathways for students, and we'll also go over some case examples. And in the end, of course, I will share a little bit more on how you can join to participate in the prize challenge as well. So stay tuned, all right? Okay, so this session is designed for those in engineering, of course, primarily, but not all. We do expect to have participants from industrial systems, mechanical, aerospace engineering, anyone interested in quantum space. I myself, I have a background in electrical engineering and computer science, but there was a time when I didn't know anything about quantum technology. So if you're in that position, that's fine. By the end of this webinar, you will understand the fundamentals of quantum-inspired optimization. Evaluate the BQPhy platform live and choose your engagement pathways. So learn how to compete for that prize that we're talking about. So here's our detailed roadmap for today's session. And what will follow immediately after this is what is QIO? So followed by Ruth's deep dive into QIO and case studies. After that, Jinwhui's showcase will move into a live demo and a hands-on simulation. So you'll see in real time how it's actually done. So you could actually try it out for yourselves. So stick with us, all right? All right, now the floor's to you, Ruth.
All right, I hope everybody is able to hear me clearly. Okay, great. Welcome everyone to this to this seminar. Just quick introduction about myself. Like Elijah mentioned, I'm the founder and CTO of BQP. Basically, the aim of BQP is to accelerate this modeling and simulation space, which I believe majority of you guys are contributing to even. And the main area that we want to, or main aspect that we want to accelerate is using advanced computing. And so that directly leads me to this slide of what is quantum computing. So whenever we're thinking about from computing perspective, classically, of course, we're thinking from to the very fundamental aspect, we're thinking about bits from zeros and ones. And if I believe majority of you may be even aware of this a phenomena called, termed by Dr. Morse, called the Morse law, which is saying that every about 18 months or so, we are doubling the size of compute for the same amount of basically the real estate, the same amount of the chip size that we have. And that has been true for several decades now. However, the implication of that is that the individual bits, the transistors, are becoming incredibly small. And so the implications of that is that directly now we're going into the quantum scale, meaning the transistors are so small that your classical physics phenomena are in essence interjecting with the quantum physics phenomena that we have. And so we cannot, and I'm sure you guys can all kind of understand, we cannot indefinitely go small and small and small. There is a limit on how much small we can go. And in essence, we are very near to that limit. And so that Morse limit is slowly creeping up on a threshold and it's gonna level off now. And so that's where automatically we transition to this quantum computing, which is again more natural way of computing. And when we are looking at quantum computing specifically, we are looking into the different phenomena of quantum physics. So it's primarily we are looking at quantum superposition and quantum entanglement. And when from a compute perspective, it is truly about how we are utilizing these phenomena to physically control the qubits so that we are able to do the certain amount of calculation that we whatever we want to do, we're able to do so. And so I'm not going to go into the quantum aspect. And actually the company was founded from the notion of, again, using quantum as a tool, right? We are not by training, we're not quantum physicists. I'm an aerospace engineer. My co-founder, he's also an aerospace engineer. We are a bunch of engineers who came together and looked at the fact that the need is there. And I'm sure a lot of you are facing the same type of problem that we were facing, where a lot of our simulations were taking immense amount of time. Even on some of the largest supercomputers, we had opportunity to work on frontier compute when it was, still coming out and such. And even then, the type of simulations that we wanted to perform was just too damn big, ultimately. And so that's where quantum really comes and plays a role. And on the left side, what you see is that there is because of the fact that quantum is still early in its early days, there's still a lot of things that needs to get figured out, from all the way from quantum computing hardware. That's where you hear a lot of these companies like IBM, Google, from the major large companies. But then you have the smaller companies like, I should say, quantum native companies like IonQ, Rigetti, D-Wave. Again, these are publicly listed companies on the market. So you have these hardware companies, then you have a layer called error correction companies. So companies who are really looking into how can we improve the quality of the way that quantum hardware are actually giving us outputs. Then you have the algorithms side of things. Then ultimately the applications, where specifically BQP stands in, is we're in that algorithmic layer where we're developing different solvers and, well, algorithms, and then creating into solvers, which then can be directly applied to the applications. And again, applications is where the for us, the end users are. And our end users are essentially you guys, engineers, researchers, folks who want to utilize this advanced computing to ultimately help them do whatever they're trying to do. And so that is, in essence, the goal of what we really want to do. Now, there is two things: quantum computing and quantum computers. Those two are, even though they seem quite similar, but they're different in nature. The quantum computers, usually we're talking about hardware. When we're talking about quantum computing, it is then fundamentally we're talking about these algorithms and solvers. And so within that, we have two different types of solvers. One which utilizes the hardware, right? Quantum algorithms that utilize the hardware. And then we have quantum algorithms that has no dependency on the hardware, on the quantum hardware. What that means is it can actually execute on current day CPUs and GPUs. And that's what basically this slide is talking about. And that area where you don't need quantum hardware to execute quantum algorithms, it's also namely called quantum inspired. And so when we talk about quantum inspired algorithms, the difference between quantum inspired and classical algorithms is that on the left side that you see usually, right, when we talk about classical computing, we have these three gates of and, or, and the last one being not. Whereas on quantum side, we have a lot more variety of gates. And what we are doing when we talk about quantum inspired is utilizing these gates, but expressing the gates as tensors or matrices. And so another way to think about quantum inspired algorithms are they're also basically just tensor operation algorithms that are just doing tensor operations. And what that then really helps is, if some of you guys are from a HPC background, you guys may be familiar with the fact that tensor operations are way more efficient to perform on current day CPUs, but more importantly GPUs, than the classical way of thinking, right? And that is what currently quantum inspired optimization, like in the area of optimization, that is where we have actually found our niche in, but also our end users, some of our end users are readily able to get the advantages that we speak of. So moving on to the next slide, the types of problems that we're talking about when we are talking from the optimization realm, the challenges that day in, day out users are facing is the fact that a lot of these problems are extremely large scale. Sometimes they're combinatorial, sometimes they're a continuous problem, but majority of them are dealing with MP hard. If you're from computer science, you may have heard this term, but they're dealing with MP hard complexity. What that means is it will, as your problem scales with more and more complexity, it will require exponentially more amount of compute in order to actually get the solution back. And so from that perspective, from classical compute, there's a limitation on what's the ceiling, what's the level of complexity of the problem that we can get to. And that barrier is essentially broken down with quantum-based operations or even with quantum-inspired optimization. And that's what it's really aimed to do. And so as you can see, specifically the second bullet, the whole approach of QIO or quantum-inspired optimization is, like I said, to utilize these quantum gates that I talked about previously, but using traditional HPCs, your CPUs and GPUs, so that we can get away from that local solution, which is what majority of the classical solvers in some sense stage that we have to accept because of the fact that we cannot get to the global optimal solution. We have to accept that. But now with this quantum-inspired algorithm, we can break that barrier down and essentially go towards that. And again, quantum inspired is, I would say, a milestone. This is not the endpoint, because even after quantum inspired is where you're gonna start coming into the utilization of quantum computers and the algorithms fitted for those. So this is kind of like the middle way that you'll be using, but this is a way for you to essentially get quantum ready and get your hands on a product that readily incorporates quantum methodologies in order to, not just for the sake of it, but in order to give you the ROI or the benefits that you seek out of it. And so that's basically the whole advantage that we are able to provide with our product, BQPhy, which again, BQPhy is the product name. It's fitted with quantum-inspired optimization algorithms itself. And so now if I can talk about specifically this optimization, the quantum now optimization is really aimed, like I said, aimed at finding the global solution. Again, if you're talking from optimization perspective, the global minima. And what that directly translates to is being able to find much more optimal solution or optimal design, sorry. Now, on one hand, you want to get high accuracy, but you do not want to spend incredibly more amount of time in order to do so, because that's always the caveat that as a modeling and simulation folks we deal with, is that we want to get high accuracy, but we don't want to spend too much time. There's that offset that everybody has to make. But now with this, we're able to get that high accuracy. And again, on optimization, it's more about the optimal solution. We're able to get the global optimal solution while also requiring fewer number of iterations. And what that directly relates to is the reduced number of simulation time. And so this is the slide, or on the left side, what you see on the slide of the Weierstrass function is, it's a very complex theoretical type of function, mathematical function, but it's a very complex function with lots of local solution. And again, local solution, when I think about optimization, I think about basically hills and valleys, right? And the goal is to find the deepest valley of them all. Weierstrass has essentially infinite number of valleys, right? But each valley is at different elevation. Our goal is to find the deepest of them all. And here what we see is that the red curve, which is genetic algorithm, which is the most popular classical optimization algorithm that you see, it's only able to get up to a certain level. And whereas the quantum inspired optimization, QIO, is able to go even more beyond what genetic algorithm is able to do. And it's able to basically find a more optimal solution ultimately. And then on the right side, what we are really talking about is the speed up. So as I mentioned just previously about being able to scale as the problem becomes more complex, but also as we require more and more iteration, the amount of time required reduces, which is somewhat counterintuitive. But that's what, honestly, that's what quantum computing is really meant for, is that extremely large scale compute. And so this is when we are putting it on NVIDIA GPUs, for example. And again, this we have shown to be on the same level of on AMD GPUs as well. But on GPUs, what we see is that as you problem becomes increasingly higher complexity, but also larger in terms of scaling, we're getting much more faster solution. So time to solution is decreasing incredibly. And that's the benefit of the tensor-based operation that I was talking about earlier as well. And so here are a couple of examples. So this is actually a collaboration that we have been doing almost a year, I want to say, where this is from a group out of Virginia Tech. We actually just published a paper on this in a quantum journal, and it should be out actually quite soon. But over here, what their aim was, it's again a material design use case. And the aim was to find atomic structure such that find a configuration of different atoms such that it is fundamentally thermodynamically stable. Meaning you create a structure of your atom or atomic structure such that your material, ultimately the overall material that you see, is as stable as possible. And so from that perspective, that's what the fitness value is really talking about, like energy levels. And the lower the energy levels, the better the stability is. So the top is what they were using classically, using classical optimization. They were only able to get about 0.19 at stake. Whereas with the quantum inspired, they were able to bring that down by about 5% to 0.018. So great, we're able to get a little bit better solution. But what helped them was the fact that we're able to get to the solution incredibly fast. And because of the fact that this discrepancy in terms of the time that we were able to provide, it's enabling them to go beyond this 10 by 10 and 50 by 50 to go into the 100 by 100 scale, where you have in total hundreds of atomic particles, that now you can do a simulation and optimization of that huge size, which currently in the world you cannot do, because of the fact that this really increases in terms of the computational complexity. And so because of that, we have enabled them to now start looking at 100 by 100 use case of atomic structure, to now even go towards 1000 by 1000. And so that is the huge benefit that we're unlocking with this, is that, of course, getting a better solution, that's definitely a really good benefit. But on top of that, how can you do even more simulation, even larger simulation than what you have even imagined before? That's really what quantum is enabling folks to do. So that's why, one of the analogies we like to think of is just quantum is not just, it's not a car versus a faster car analogy, but rather a car versus an airplane analogy, where cars you can only transport from one place to another, but with aircrafts you can do that, but you're able to go much more beyond the capabilities of what a car can do. And so it's a whole new way of thinking as it may. And talk about aircrafts, this is the second use case that we are doing, which is on aerodynamic optimization. And again, this is with another university out of India, actually, in this case, where specifically we're looking into how can we optimize the shape of this. We are looking, teardrop shape that you see, that's actually the shape of a wing. And we are looking at how can we change the shape of the wing such that it is as aerodynamically efficient as it can be. And so what we are able to do, again, our benchmark is classical and classical benchmarks. So when we are comparing both of the things together, the things that we're looking at when we talk about aerodynamics are lift and drag. So we're able to increase the lift slightly, but what usually ends up happening is that lift and drag, there's a trade-off. The higher the lift you go, the higher the drag you produce. You have to, in some essence, make that trade-off, and then you have to kind of find a balance in between. And for this case, starting from this shape that you see at the top right, we started with that. And compared to the classical one, we're able to increase the lift slightly, but more importantly, we're able to reduce the drag significantly to overall improve the entire aerodynamic characteristics of this wing, so that you are able to get, if this was to, let's say, put into production facility by Airbus or Boeing or whatever, they would be able to use less fuel because of the fact that it is a less drag, hence you need less fuel to operate. So you're ultimately helping the overall design and the design characteristics using this type of optimization. And so these are some of the use cases that we have already performed with our partners, but there's a lot more beyond this type of design type of use cases, you can do a lot more as well. Here are a few other cases that we have talked about, that we are presenting, where we have previously done a couple of use cases that are related to supply chain, and specifically when we are talking about the distribution network, right? In the modern world, the distribution network of these big conglomerates like Amazon, for example, they have so many different distribution centers and warehouse facilities and such. Their network is truly a nightmare. But when we are talking about extremely large scale, at that scale, the level of optimization that they are performing and the amount of compute that they're using is ridiculous. And why? Because of the fact that any small, even 0.5%, is going to save them billions of dollars. And so that's where this optimization, of course, is really important part of any industry. But more importantly, the quantum inspired optimization is going to be able to break those barriers on what you can do up until now and to go towards a lot more. In today's world, using just CPUs and GPUs, you don't need quantum computers to do so. Another one is, of course, when we talk about, again, aircrafts and the structural limits of it, how can we push the boundaries on that? And lastly, the other one is scheduling, which is something we'll show a little bit later as well. But this is a very, very classical classical problem, NP-hard problem, where as you increase the complexity, there's a lot of problems like job shop scheduling, nurse scheduling in a hospital. All of that is a nightmare to do so. But now with quantum inspired optimization, it can actually, in realistic time periods, can be able to get a better or more optimal solution than what these folks have been basically exposed to up until now. So with that, I'll pass it over to one of our collaborators at University of Maryland, Jinwhuy. So yeah, take it away, Jinwhuy.
All right. Thank you for the introduction. Anyway, I hope everyone can hear me well. Okay. Well, yeah. Hi, everyone. I'm Jinwhuy Lee, and I've joined University of Maryland Alfred Gessel Rotorcraft Center since last September. And I'm really glad to share our recent research in this webinar. So our research mainly focus on the rotor blade optimization using the quantum inspired optimization. And so let's start with the rotorcraft. So what is the rotorcraft? So as you well know, like helicopter is also a rotorcraft, and a rotorcraft is an aircraft with a rotary wing. So with these rotary wings, a rotorcraft can perform hover in contrast to the fixed wing aircraft. And these rotary wings have like different platforms. And as you can see from the right figure, there could be rectangular platforms and some tapered platforms, and even some has the swept tip platforms. Then what are the challenges to optimize the rotor blade? First, the design space is large and nonlinear. Normally, like airfoil, if airfoil is considered, like 2 or 3 airfoils are used. And if we also consider platform variables, the number of the design variables would be above like 50. And also, if you look at the right figure, design space is typically very nonlinear. So we should use the gradient-free algorithm to optimize the blade. And even worse, to evaluate the single blade geometry, usually takes more than 5 minutes to run with mid-fidelity solver. So if we use even high fidelity solver, it took a day or a couple of days to just get the single evaluation. I can say that in rotor blade optimization, it is really crucial to reduce the number of evaluations. And usually gradient-free optimization, such as NSGA, is widely used to optimize the blade geometry. But however, if small population is used for computational efficiency, premature convergence can be happen. So therefore, the goal of the research is to replace NSGA to quantum inspired optimization for global exploration and also the faster convergence. As a case study, quantum inspired optimization was applied to Rastrasian function. So Rastrasian function is a function like this. For the case study, d in the equation was set to 2. And for design exploration, set maximum generation to 100 and population to 10, 50, and 100, 200. So now look at the optimization result. And here, the lower means the better solutions. And as population decreases, GA, which is the red line, converges to the local minimum. and while QIO still converge to the global optimal solution. And we can also see that the standard deviation of the QIO was much smaller than GA, which means that QIO performs better regardless of the random seeds. Now, we've checked how QIO performs well in rastreating functions. I'm gonna move on to the rotor blade optimization problem. And here, the baseline blade was set to a hard-to-rotor blade, which is a model-scale blade of BO-105 helicopter. And the blade is hingeless and has a rectangular platforms, and you can see the other specifications at the right table. For the blade analysis, UMAC2 was used, and UMAC2 is a Rotorcraft comprehensive solver developed by University of Maryland, and it offers various fidelity of aerodynamic solver from low fidelity to mid fidelity. And UMAC2 is validated with various experiments, and if you can see the right figure, you can see the validation result with the experimental results. For the design problem, we are currently focused on the hover performance as CP over sigma is equal to 0.1, which is equivalent to 1,582 newtons of thrust. And the single objective function is used to maximize the figure of merit, which is the hover efficiency. And note that the large figure of merit means the better hover efficiency, which means the lower power consumption. And we use 4 design parameters, so 2 twist distribution and 2 core distribution, which is quite simple as a case study. For the optimizer setting, we set like maximum generation of 30 and number of population of 30. And we ran the simulation with 15 different seeds, and the initial population of GA and QIO was maintained to be the same for both methods, which is to compare the effectiveness of the optimizer. Okay, so here you can clearly see that QIO does serve the better objective than GA. Here the higher objective means better. And since it's in the right figure and you can see the optimization history, the scatter points represents each evaluation and filled by number of generation. And it's clear that QIO does explore more than GA and resulting to find a better objective. Before we move on to the next, I think it's better to understand how design space looks like. And since it's like 4-dimensional design space, I fixed design variable 1 and 2 to 0.1 and 0.2, since the most of the final objective results were located at this black box region, and see how objective changed with design variable 3 and 4. And now you can see the design space is very nonlinear. So for design variable 1 and design variable 2 to 0.1 and 0.2, the best objective is located at the bottom left corner. And so we can see the capability of exploration is much more important to find the optimum blade design. And among the 15 different seeds, so I plotted the results from 3 different seeds. And here the optimum blade design at like each generation is plotted with black, and the final objective blade design is plotted with red. And when compared with GA, we can see that the design space is more densely filled for quantum-inspired optimization. And these trends can be observed for entire 15. If we look at the final objective value, the QIO mostly outperforms GA. So red color represents the better objective. And even some seeds where GA outperforms, the difference between QIO and GA was really small. So here's the conclusion of the research. For the rastreating function case, I'll better explore the design space with smaller population. And for a blade optimization problem, QIO can explore more than GA and resulting in a better objective. So with these case studies, we confirm the efficiency and the capability of the design space exploration of quantum-inspired optimization method. Our further work includes expanding the design space, including the error parameter. And also we're trying to apply the quantum-inspired optimization method to multi-objective problem. Thank you for listening. And if you have any questions, just please feel free to let me know.
Thank you, Jinwhuy. Before we move on to the next slide, I just want to open the floor just quick to see if anyone has questions, maybe for Jinwhuy or even Ruth as well. If you do, just pop a question in the Q&A, and then we'll review it and then we'll come back to you. So with that, I'm glad actually Jinwhuy just ended this with the rastrogen function because we do have a sample case today which you'll be able to try that has the case example for the rastrogen function. And for those of you who might not be too familiar with the rastrogen, this is a way to check how robust your algorithm is in a very complex computation. So you will have that opportunity. So please bear with us. And moving on, today, the way how you could join us to fully participate is not just listening into these amazing speakers, but also to try it out yourselves, right? So we do have two different paths for you right now. So we have the Explore track and we have the Innovator track. The Explore track is just for someone at a beginning level who just wants to try it out, just explore the tool. Like I mentioned, we have 6 case examples, 6 different types, which are Honorable BQPhy has provided. So it's very easy. You just have to install the package, which we will show you at the very end. And you can actually try the BQP technology itself. You'll just import it on your VS Code or whichever environment that you use, and then you could actually launch it. So let's see how that goes. In the meanwhile, after you've tried that out, of course, after you do the Explorer track, you get a small certificate as well. But after that, if you really want to engage, if you really want to try this tool that BQP offers, which is not available to everyone, you will have exclusive access to this by participating in the Innovator track. So what happens here is you actually get to invest 3 to 4 weeks from now, actually draft a project proposal, and please share it with us using the BQP tool. You could share just like what Jinwhuy did. You could try the quantum-inspired optimization to see if there were some aspects of your current project that you're working on right now, which you were able to fulfill with the BQP's optimization tool. So if that's the case, just submit your project after 3 to 4 weeks, and then you will be able to participate for a prize pool. So we do have the first prize, second prize, and the third prize, just like the Olympics. So just keep that in mind. And we're going to switch our gears, moving to the actual live demo. So Ruth here is going to present to you how the BQP actually works. So I will leave it up to you, Ruth, and we could go from here.
All right, thank you. Actually, slight change in the plan. Roopesh here, who is our VP of Product, Dr. Roopesh Mathur, he's going to be doing the demonstration. So yeah, Roopesh, if you can share his...
Yeah, I will do that. Hi everyone, my name is Roopesh. I lead the product team here, so I hope many of you have got the chance to download the Python library that was shared with you, or will get a chance to download in a little bit. So what I'm going to do is to just do a very basic demo of how to install it and how to run it, how to run a simple problem. And I'll use a Jupyter Notebooks server to, as well as a Jupyter Notebook on my laptop to actually show you an actual application. So I'm going to share my screen and then let's get going. Okay, so when you actually open up the package that was provided to you, you'll get essentially a wheel file, a license key, and a user guide. So you can open up the user guide and read it, and it will give you some guidance on how the whole thing works. Today, what I'm going to do is to just install the wheel file that is relevant for my laptop, and then I'll actually run a case. So if you look at this wheel folder, we have actually 4 wheel files. So 2 for Python 3.10, 2 for Python 3.12. So those are the 2 Python versions we support. And then 1 is for Linux and 1 is for Windows. So we have Python 3.10 Linux, or Python 3.10 Windows, 3.12 Linux, and 3.12 Windows. And because my laptop is a Windows machine, I'll set it up on my Windows machine. So I already have my virtual environment that I've already got set up. I'll call it Wiser environment. Not a very creative name. And I'm going to use standard Python install. So I'm going to say pip install, and I'm going to say wheel, and because I have BQPhy 3.12 Windows, so I'll just go to that one. So this is what is relevant wheel file for my Windows. So I'll just run it. So then it installs, and then after that I'll show you guys in my Wiser environment where the site packages folder is. There are some examples. So we'll just copy over one example, and then you can actually use it. So yeah, so I think it installs whatever is needed, and then it will come up. Just give me a second. It will installing it. I'm going to go to the Wiser environment, and you can see in live site packages, you'll see BQPhy show up at some. That's going to take a little bit of time to do. And while it's doing that, I also want to show you the license file here. So we have in the license file, if you go to the webinar package, you'll see this as a license file. So the way we do licensing is that this is just a token and it's valid for 1 month. So it should be valid until the end of April. And you can just use this token as part of the licensing installation, which I'll show you in a little bit. Yeah, so let me just go back. It's still doing whatever it's doing. But the basic idea is that we will actually install this package, and then we will install the license, and then we'll run a simple example. I have a Python notebook. I'll just use that Jupyter notebook to run a case, right? And I think if you have any questions about any of these, any of the steps in the installation, please type it in the questions window, and I'll be happy to take questions. It's taking a little bit of time to do this. Okay, yeah, it's ready now. So this is what I'm going to do. If I go to my Visor environment and then I look in the live and site packages, and I go to the BQPhy folder, which is here, you'll see some folders there. So here's an example. So there you can see there's lots of different examples. So the continuous Rastrigen function that Jinwhuy just showed, it is an example. So let's just take that, and I'll just go to copy. And what I'm going to do is to bring it to my webinar folder. I'll just copy it here. And then what I'm going to do is to just run this, right? So just like you run any other Python file, you run this, which is called continuous Rastrigen. And then it says, hey, where's your license? So then at that point, you go to the license, this token, this small token that you have, alphanumeric token, you copy it, paste it, and it will basically then install the license and it will run that, right? So that's basically what it's doing. I think I need a file. Just give me a second so you can see. So I think one of these files, Rast pop in it. So you can initialize your optimization with an example. So I'll just do that. Yeah. So I'll just put it here, and now I'll run it again. So you can see that it actually ran, and then it did the optimization. Okay, so it's fairly straightforward. So you install the license, you take some of the examples from the site packages folder in the BQPhy folder, and then you run them just to get yourself up to speed. So it should not take you that long to do that. And so that's basically what you're doing. So everything that Jinwhuy did, you can also do it yourself. Very, very easy to do. And there's several other examples. Now, what I'm going to do next is to launch a Jupyter notebook, and I'll read in. So I already have Jupyter notebook installed on my laptop. So I'll just install it, and then I'll also read an application that come up. And what I have is that in my folder, I have a problem, industry problem that I've solved. So I'm just going to copy it in there. Let me just do that right now. And I'll just copy it in there, and then I'll open this up. So you can see it's here, and then I'll move this up. So I'll open this. Yeah, so this is a Jupyter notebook, and it has a lot of different, elements, cells in it. We are explaining the problem and so on, so you can see how this is done. So I'll just do a quick walkthrough as I'm executing this. So here's my import capability. So here's multi-satellite mission scheduling. So this is actually the scheduling of satellites for orbit around the Earth. And then so this is the introduction to the problem. This is a very complex problem because nowadays there are many, many satellites being launched. So many of you know, for instance, that the Artemis mission launched yesterday. And one of the very first things it did is to unload a whole bunch of, CubeSats or nanosats into orbit. So that's what it did. So nowadays there are many more rockets being launched, many more satellites being launched. And so how do you take those satellites, and how do you ensure that they're used in the best way possible? So this is what this problem is that we are solving. So it's a fairly complex problem, and we are solving it using QIO. So these are the packages that you need, and these are to solve that. Some of them we already installed, some of them it will install as needed. So if you look at this, there's an installation step here. So I'm going to just have it go through, and it will, it will give me a message at some point. And while it's doing that, I'll also give you guys a walkthrough of the mathematical model. So here we are looking at number of satellites. So you have an index for each satellite. We have an index for missions. So, a satellite can have, or all these satellites can have multiple missions being assigned to it. So for example, some are ASAP missions, that is that you want to take a cyclone or a hurricane or a fire or some emergency situation, and you want to take a picture of it as soon as possible, right? So you want pictures being taken as soon as possible. Some of them are more longer term. So if you want to look at forest cover, for example, if you want to track forest cover, you want to take a picture every day or every few hours so that you can see how the forest cover changes over a period of time. So you'll see different missions or different urgency. And then each satellite carries some resources. So it carries some sensors, it carries some cameras, other payloads that are there. And those resources are used to execute on the mission. And so we actually look at the whole problem as a set of resources to be executed to accomplish those missions. And what we do is we also look at, what's the earliest time, allowable start time, latest allowable start time, how much is the duration of the mission, and priority or value of the mission. So the ASAP mission is higher priority than something that you want to do every day, right? So that's basically what it is. And so we then do the rest of the optimization problem definition, and then you can see that we've set up the parameters for the satellite. We set the parameters for the problem. Here we have 10 missions, 2 satellites, 4 resources, and 30 hours, basically, or 30 time units. So that's the scheduling. So then I'm going to also import a path here of another file. Just give me a second. So I have my notebooks folder. So I'll go to my notebooks folder and I will import a path. Just give a file here. So this is my data sets. I'll import, this is the mission scheduling data. So I copy. So I'll go back to Python and I'll put this new data set here, which I need. And then I'll go back to my notebook folder. Yeah, and then I'm going to just import this here. So it's importing that, and then it's going to import other things, other information that's needed, and then it sets up the decision variables, which is what a satellite is used for which mission and when. So it sets all of those things up, and then after that we move ahead to the actual problem. So here's my objective function. Here are the constraints and how many decision variables are there, and then I define the fitness value for the function, and then we basically look at how many decision variables are needed here, and then we finally run the quantum inspired optimization. So this is basically what we are doing. So I'll just run the notebook here, and it will actually take a little bit of time, and then it will run everything for me. So this is where we set the configuration for the optimization. So I'll just show you where we set the configurations. So yeah, so you can see that we are running. So each problem has different number of design variables. So we say we need the population size to be roughly 4, number of generations, delta theta, which is the parameter we use. And then we say this is a primary optimization, binary design optimization problem. So then we actually run this, and then we'll get the answer in a little bit. So I think that let's see where we are actually. So I'm going to, yeah, so while it's running, I can take any questions. I think, Elijah, if there are any questions, just let me know.
Yeah, so far, I don't think we have any, but if anyone has questions, feel free to just pop it out in the chat. That's also fine.
So they were
And I
asking
think
if they will be having like any notes.
Yes, so that I can answer. We do have, well, let me answer the first question. We do have this step-by-step instruction, which I will go through with you together after Roopesh has completed his demonstration. So it's completely fine if you're feeling a little bit lost, don't worry. There is a step-by-step learning guide for this. So we'll go over it in the end. Please bear with us. The next question, what about package for Mac devices? Yes, actually, I did ask about this question. Unfortunately for Mac users, we are working to get the real package right now for Mac. We can send it to you possibly after this session, which you could try it out for yourself. But in the meantime, we have the real packages only for Linux and Windows. Correct me if I'm wrong, Udbhav. Feel free to jump in here.
Yes.
And another question, is this project only for aeronautical background students? Anyone wants to take that, Roopesh, or should I just answer that?
I think that I can answer that. No, we are not limited to aeronautical background students. I think the important thing is to have the problem that you want to solve in the right way. So any problem that has combinatorial complexity is characterized by large numbers of variables and has a non-convex design space. That is, it has a problem that cannot be solved so easily by conventional methods. I think that would be a good candidate for us. So it can be anything actually. So we've looked at, for instance, financial portfolio optimization, stock picking. We looked at biology problems. We've looked at AI/ML training. So lots of different things are possible here.
Thank you, Roopesh. And I think we have another question. Why doesn't this support 3.13 Python on 3.14?
Yeah, so that's a good question. Actually, the main thing is that when you build a product, you have to be sure that it works for that platform. And so we go through extensive testing for these Python versions so that it will run and we can be 100% sure that it will work with those Python versions. As many of you know, sometimes with Python versions, there's a big jump in what is possible. So if you look at like 3.7, 3.8 to 3.10, there's a big jump or a big change in terms of the core capabilities, in terms of the numerical libraries like NumPy, SciPy that we use. So there's sometimes those changes make it difficult to actually run the underlying algorithm, which is a math algorithm. In the end, it's a mathematical algorithm using quantum principles. So basically, that may not be supported by that version of Python.
Thank you, Roopesh.
That said, we are looking at making it agnostic to the Python version. It's very hard because we have to guarantee that it will work for every Python version out there. So that's very hard to do.
Yes, trust me, I've also gone through the same struggle. You do have to install Python 3.1 or 3.12. So please bear with us on that. And the last question here is from Eric. Does the BQPy library automatically handle using GPU if available, or does that require configuration?
I will show you at that point. So let me just go and open up my, I actually have a Jupyter server, so I'll show you guys how it works. So this is my handy dandy server. So I'll go and I won't use it here, but I'll show you the example. So this is your continuous Rastejan example, for example, right? So if you go here and when you run the solver, there is a way to actually specify whether it's GPU or not. And actually, I'll show it in mission scheduling itself. So I think that's, so for instance, here, what I can do is, I'll just do a quick search because there are many, many cells here. Yeah, here. So when you do optimizer run optimization step, this is this step. And here you can say, instead of OpenMP means that it's using multi-threaded cores, you can say GPU, and then it will run on that GPU. Okay, so that's really, and at this moment, we support only NVIDIA GPUs.
All right, thank you, Roopesh. And there is one more. Degree students were allowed. I am completely under the background of Bachelor of the Computer Application. And can we do a project like a repeated one on a repeated theory in the background? So Preeti, I'm not sure if I'm understanding your question correctly. Diane, if you can grant Mike access, I want to see if he could just share verbally to clarify on his question. Please give us 1 second, Roopesh. Yes, for the Google Drive folder.
So my question is like, I'm completely under the degree background. So we are like looking over in Aditya College. So we are taking up a project on aeronautical engineering only about the qubits. Can we do the project repeatedly over in this, or we have to do a new project like inventing something new for you?
Okay, I think you're, yeah, go ahead, Roopesh.
Yeah, so it depends on the problem. So Preeti, I think that what we expect is that we will give you the optimization tool, but the actual problem, like the shape design problem that Ruth showed, you have to actually implement the function for the actual problem within your within your system, and then we can show you how to connect it to the BQPhy optimizer here. So if you're solving that problem, what you can do is that you can set it up, and then you can connect the BQPhy platform, and then you can run it. And one thing I think you mentioned repeatedly, so you can actually specify a starting point. So for example, here's my starting point, right? So Rust init, I have the same starting point, right? So you can see I have the same starting point here. So that starting point you can specify. So you have 4 variables, and these I have 15 members, 15 starting designs, and then these are the values. So you can specify that, right? So if that helps, I'd be happy to take any, if you have any questions, we'd be happy to work with you actually on your project.
Okay.
Just to add on to this, I think after the webinar, we will be sharing a Discord channel link with all the participants. So if your queries are not getting resolved right now during the webinar, we can use that as a forum to constantly support you during this journey. And your queries can be resolved over there as well.
Okay, thank you. I think just for everyone's information, I did share the Google Drive link again, so it should work now. And Roopesh, I think we can close your screen share if that's okay and move on.
Thank you.
Okay, thank you, Roopesh. All right, so let me share the screen once more. So thanks to Roopesh, we've just gone over a live demonstration of how this BQPy actually works. And now we have about little more than 20 minutes right now. Our next step is to actually do a hands-on simulation with you. We will like you to get involved and go through a step-by-step. But before that, I just want to recap that we do want you to have the opportunity to participate in the innovator track. So this is where you actually get to submit your prizes. And oh, I see the date is not updated here. Sorry. Please sign up by end of this week. And you should be able to submit your project by April 10th. Sorry, it should be towards the end of the month. So that I think it was April 27th. My apologies. And we're going to be following up with those who actually participate so that you are kept in track. And if you need any support, if you need any mentorship, if you need any guidance, we will connect you with our team in BQP. So with that, we're going to move on to the individual simulation. So I think this is the part where you will actually be able to try it yourself. And I think this is where we could actually stop the recording as well. And this because this will be individual practice, but here we'll have Roopesh and Udbhav and myself who will be helping you figure this out yourselves. And in the meantime, I just want to check with Jinwhuy and Ruth if they're still here. Jinwhuy, Ruth, you're welcome to stay on, but I'm sure you're quite busy with everything that you're working on. We just want to thank you for being here today with us, having to share what seemed like a very amazing project that you're all working on. And it's good for everyone to learn what you're doing as well and how they could experiment with this tool, having to demonstrate something what you're doing as well. So thank you again. And feel free to stay on or feel free to leave. And we hope to see you again in our next webinar. Thank you, Jinwhuy. Thank you, Ruth.